chapter. So we have chapter 3. Let me see if, okay, here. So here we have chapter 3. So we discussed matter already, and now we are going to look at energy. So let me ask you, how many different types of energies do you know? What are the different types of energies do you know? Different energies, the names of different energies that you guys know. Yeah. Different energy types. Potential energy, very good. So one is the kinetic energy. Potential energy. And just write down in the chat. Thermal energy, very good. So that's heat energy. And mechanical energy, very good. And petroleum is like a chemical energy. Okay, good. What else? Yeah, coal is petroleum. It's coming through the chemical processes. Okay, Marcus. There is light energy. There is sound energy. And then there are other sub-energies also. I mean, the heat, mechanical, then comes mechanical, heat, light, sound, chemical. Then there is electromagnetic, and then there's just electrical energy. Okay, then we all know solar energy. Then we know the wind energy, right? Then there is atomic energy or nuclear energy. Okay, atomic, excuse me, atomic energy. And then there's nuclear, coming from the nuclear power points. So these are the common ones, right? The common ones. So all these are like common energies. So in this case, these energies have certain measurements. Energy is anything that allows us to do work. Some kind of work is performed. Anytime there's a energy is, so energy cannot be created, energy cannot be destroyed, but energy can always be transferred from one form to another. So if we see the, you can convert the heat energy to light energy. You can convert light energy to heat energy. You can convert the solar energy to light energy, right? You can convert the wind energy to mechanical energy. You can convert the chemical energy to mechanical energy, right? So that's the transformation is happening. And so let us just focus on these two things right here for now. What is the kinetic energy? Kinetic energy is energy by which substances remain in motion, okay, moving, okay. Potential energy is by which substances remain at rest. So when substances remain stationary and don't move, that is also energy is holding that, and that is called the potential energy. And then the other one is the heat energy. So commonly, and then there's chemical energy, but there's bond energy, those things. So heat energy is the thermal energy, which comes by, exchange of heat. Okay, so these three. So now let's look at the units of energy. Units, how do you measure these energies, especially the heat energy? Okay, so units, just like you have the units for like, temperature and pressure and length and mass and volume, density, specific heat, specific gravity, those things. The same is the case, we will have these energies for, different energies are measured. So here we are looking at the heat energy. So units to measure energy, and this energy in our context is the heat energy, and this is also called a thermal energy. Okay, thermal. All right, now we are going to look at the units. So 1 small calories is equal to 4 comma 184 joules, Joules. And this one small CAL, I'm going to just put this here, J. So CAL stands for, small CAL stands for calories. CALORIES, calories, okay? And J stands for joules, JOULES. And this equality can be converted into two conversion factors. One, small calorie over 4184 joules, or 4184 joules over 1 small calorie. Okay, so these are the two conversion factors. So this is one set. Okay, let's just put it here, one set. Now let's look at another one. If you have kilocalories, then what's the story? Or kilojoules. So here you have 1 kcal, small cal, is equal to 1000 small calories. Okay, and 1 kilojoules is equal to 1000 joules. So this is the basic, conversions. Now the same thing can be written as this thing. This can be written as 1000 calories. So it's going to be just CAL, and this is J. So I don't have to use so much space. So 1000 calories over 1 kcal, or 1 kcal over 1000 calories. Okay, this guy over here can be written as 1000 joules over 1 kilojoules, or 1 kilojoules over 1000 joules. So these are the conversion factors coming from these. Okay, now let us see, you are given this problem. Okay, so here is this example, page 74, page 74. Okay, page 74, and this is the study check problem 3.5, and that is when 1.0 grams of glucose, this is the glucose, is metabolized in the body, it produces 3.8 kilocalories of heat. How many kilojoules are produced? The question is, how many kilojoules is this? Okay, so 1 gram of glucose is producing 3.8 kilojoules. So this becomes equal to that. Okay, so this is how you read the question and then you write down. So here this thing becomes 1.0 grams of glucose over 3.8 kilojoules, kilocalories, okay, or 3.8 kcals over 1.0 grams of glucose. So these are the conversion factors. These are called conversion factors. Conversion factors, okay, of this. So, oh, I'm so sorry. Okay, sorry about that. Okay. All right, now we have the, 1.0 now we are given the what was it? I forgot the question. How many kilojoules are produced? So okay, so now we need to convert this kilojoule. We need to convert the kilojoule. So kcal. So 3.8 kcal. Convert that to kilojoules. So 3.8 kcal. Convert that to kilojoules. So how would you do this? So what do we know? We know that 1 kilo. So this is in kilocalories. And this kilocalories and relationship of kilocalories and joules. Okay, so we know the relationship here of calories and joules. Calories and joules, right? And let's convert the calories to kcals first because they want it in joules, kilojoules. They want it in kilojoules. So we are going to convert that to kcals to calories. Sorry, let's do kcals we already have. And where did it go? I'm sorry, I got distracted because of those phone calls. 1 minute. One kcal to kilojoules. Kcal to calories and calories to joules and joules to kilojoules. Yeah, we could do that. Okay, let's do this way. Kcal to calories, calories to joules, and then joules to kilojoules. Okay, so 3.8 kilocalories. So what do we know that 1 calorie, one kcal, 1 kilocalorie is equal to 1000 calories. Okay, so that means that we can convert 3.8 kilocalories to 3.8 kilocalories to calories. Convert that first. Okay, so how do we do this? So we'll write down what is given to us, which is 3.8 kilocalories times the conversion factor. Now, anytime a conversion factor is set up, we are going to remove the kcals because we want to convert kcal to calories. So the units that you want to cancel out goes in the denominator, and the unit that you want stays on the top. So here you see that 1 kcal is equal to 1000 calories. So this step cancels out the kcals and you're left with the calories. So 3.8 times 1000. And how many calories is that? Yeah. 3800, very good. 3800 calories. Okay, next is you're going to convert these calories to kilocalories. No, sorry, to joules, sorry. Next is the relationship exists between the calories and joules. One is this and the other one is this. So we know that 1 calorie is, so write this down, 1 calories is equal to 4.184 joules. Okay, so we have 3800 calories, and now we are going to convert those calories into joules. So you're going to write down the unit of joules on the top because this is the unit that you need. You want to cancel out the calories because we want to convert the calories to joules. So when you put them in denominator, they cancel out. Okay, so we know that one calorie is equal to 4184 joules. Okay, so now you are going to, you see that calories and calories cancel out and you're left with the unit of joules. So now 3800 times 4184. And you get 15,899,200. Okay. Now, actually it is, here's a mistake, guys. 1 minute. That doesn't make sense. This is point. Yeah, this one is point 4.184. 0.184. Okay. Yeah, I know that's a lot, but this is 4.184. So just do it back again. So 3800 times 4.184. Yeah. And that gives you 15,899.200. Okay. So these many, that's the joules. Now we have the joules. Okay. Now we are going to convert, the third step is to convert the joules to kilojoules. Okay. So 1 kilojoule is equal to 1000 joules. All right. So now you're going to write down 15,899.20 point. This is point 20 times, this is this was joules, times 1 kilojoule, that's what we need, over 1000 joules. Okay, so now you cancel out the joules and joules and you're left with the kilojoules. So 15,899.20 divided by 1000. Divide by 1000 and you get 15.89. Okay, and you can round this up to 16 kilojoules. Okay, got it? So you see that anytime you are trying to work with the equalities, you create the conversion factors. And these conversion factors are done because we are trying to use them in dimensional analysis. So in this case, in the dimensional analysis, by dimensional analysis means that you basically cancel out the units that you don't want. Okay, now Alex is asking a question that if all the numbers in the equation are exact, where do you round off the solutions to? The last answer. The absolute last answer. I mean, this is obviously more precise, more exact number, but it's okay to, round up the last, round up the answer, the final answer. So in other words, what we did was all these steps in the middle, okay? All right, next is, let's look at now, energy values and food. Now comes the energy values and food. Okay, energy values and food. So here there's a little bit difference. So we know that 1 kcal, that's a small c, is equal to 1000 calories, small c, right? But this is equal to 1 big C. And this C, a capital C, capital C is the nutritional calorie, the one that you derive from the food. So this is the nutritional calorie. I mean, calories are basically the values for the heat, right? The heat energy. And you can get the heat energy from, so many different things. So this calories is basically this big calorie, big C is the nutritional one that comes from the food when you metabolism of the food. Okay, so here, for example, this whole thing can also be written as one big calorie, or in other words, look at this here, 4.184 kilojoules is equal to 4184 joules. Okay, and this is equal to one big calorie with a big C. Okay, so I'm making it on purpose how this is done. All right, now let's look at from the food. How do you get that? How do you get? All right, here's the thing. You see the food labels, right? On the food labels, you see that here's a typical, here's an example of a food, is an example of a table. Here is your example in the book on page, this is 3.7, and this table is page 77. And so here, this is giving you from carbohydrates. So I'm going to just put it CHO, from fats and from proteins, PROTEINS, from proteins. So from carbohydrates, we see 4 kcal per gram. Per gram means from 1 gram of carbohydrate, you would get 4 kilocalories of energy or heat. From the fat, from 1 gram of fat, you are going to get 9 kilocalories of energy or heat. Proteins, from 1 gram of protein, you are going to get 4 kilocalories of energy. Okay, and same thing in the joules, it can be 17 kilojoules of energy is obtained from 1 gram of carbohydrate. 38 kilojoules of energy is obtained from 1 gram of fat, and 17 kilojoules of energy is obtained from 1 gram of protein. Okay, so this is, you will see this is like a typical energy values of the food types. Okay, now let's look at this example. Study check. This is study check. 78 page and 3.6 problem. Problem 3.6. Okay. Using the nutrition values for one serving of crackers in sample 3.6. So this is something we will look at. The same table that is on the top right here. This table. Okay. Calculate the energy in kilojoules for each of the food type. Round off the kilojoules for each food type to the tens place. So what is the total energy in kilojoules serving from the crackers? So here it is. So let me just write this down. So here is this problem in which they are saying that there are crackers. Okay, a box of crackers has this label. Crackers, CRACKERS. Okay, a box of crackers. The nutrition food labels for crackers states that one serving contains 19 grams of carbohydrates. So CHO is the carbohydrate, 19 grams, okay? 4 grams of fat. 4 grams of fat is present in this one serving of cracker. And there is 2 grams of protein. 2 grams of protein is present in one serving. What is the energy of each type of food? And in this case, they're saying find it in kilojoules. So in kilojoules, how many kilojoules is energy are you obtaining from fats, proteins, and carbohydrate? Okay, so the way you're going to set up the problem here now is you're going to write down it in a tabular fashion. 19 grams fat, 19 grams of carbohydrates, 4 grams of fat is present in that one serving of cracker, and 2 grams of protein is present in that one serving of the cracker, times, times, times. Now you are writing um, the values. These are the values that are given to you in the table 3.7, page 77. So from carbohydrate in kilojoules, you would get 17 grams, 1 grams of 1 grams, so this becomes your conversion factor. So 17, so this becomes 17 over 1, 17 kilojoules over 1 gram. Same is the case, 38 kilojoules over 1 gram for the fat, kilojoules over 1 gram, and 2 grams, 17 kilojoules, 17 kilojoules over 1 gram. Okay, so this allows you to cancel out the grams, 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 and you're left with just the kilojoules. And just do the math now. So each of this, so this is 19 times 17. This is 4 times 38. And this is 2 times 17. So get the answers here. 19 is 323 kilojoules. Okay, 323 kilojoules. What about fat? Fat is 152. Thank you, Tenzin. 152 kilojoules. And protein, 34 kilojoules. Excellent. So next question is, find the total that you're going to obtain from that cracker, 1 gram of crackers, or whatever, 1 serving of crackers. How much is that? You add all these up. Add 509. So you see 509 kilojoules of energy is obtained. So, I mean, your book is giving you something similar, but it's 500 kilojoules, or maybe they, I don't know what they brought up, 320. Yeah, so anyway, so this is 509 kilojoules is the energy that you get from the cracker. So this is how, on the food labels, this is on the food labels, all this information is written that from 1 serving, you're going to derive this much of the nutritional, value. So it's always a capital C, okay? So this is one piece. Now comes the next piece. Now we're all talking about just the heat. Specific heat. Every substance in this world has a capacity to absorb some amount of heat. Okay, and that is called a specific heat. That's why the name. So the specific heat is defined as the amount of heat that is needed to raise the temperature of exactly 1 gram of a substance by 1 degree Celsius. Now let's look at this one very interesting examples here. So let us look at this. This is one test tube, or not the test tube. Let's just put it here. This is one let's say cube made up of aluminum. Here's another cube that is made up of iron. Another cube that is made up of silver. Okay, and another cube that is made up of copper. These are just some examples I'm giving you. Okay, so these are, and here you put the thermometer. These are just the thermometers in each of these. And let us say these are all 1 gram. 1 gram of aluminum, 1 gram of iron, 1 gram of silver, 1 gram of copper. You've all seen aluminum as aluminum foil, iron, iron foil, iron, like objects made of iron. You've seen it in your life. Silver, like silver rings, silver jewelry, and then copper wire. So you kind of have an idea what they look like, okay? Now this is the temperatures. You have put the thermometer in them, and now you start heating them. Okay, now you start heating. So you heat this here, you heat this one, you heat this one, and you heat this one. So you're basically heating all of these. Okay, so now when it gets heated up, remember, all of them are 1 grams. So we want to see what the temperature looks like. You are all heating them evenly, you know, all of them 1 gram, all of them are being provided the same amount of heat, even though this may look like a little bit, you know, same amount of heat. So no difference there. And what happens is that they all have a capacity to absorb different amount of heat. Okay, so the temperature begins to rise for in each of these cases. The temperature rises, but it rises, you know, at a different rate. Some of them are going to catch heat quickly and very quickly get hot. So we will see quickly rise in temperature. And some of them, we are going to see the rise in temperature slowly and slowly, right? So what is happening here is that it is the specific, it is the nature, specific heat. And that is actually called a specific heat capacity of every substance is very unique. Okay, is the amount of heat that is needed to raise the temperature of 1 gram of that substance. And when it absorbs the heat, we would see, you know, how quickly it is increasing. It is showing the increase in the temperature. 1 gram of that substance and how quickly it shows the increase in temperature by 1 degree Celsius. Some of them are going to take very long to show the increase in temperature. And some of them are going to show slowly and slowly, you know, that so how if you see the increase in temperature fast, that means it's absorbing the heat fast. If you're showing the change in temperature very slowly, that means it's slowly, you know, absorbing heat. So this heat capacity is low or slow if you see slow rise in temperature. So this is how you measure the specific heat. But in the formula, here's the formula. Generally the specific heat formula is specific heat is the SH, okay? And then it also, other terms also, SH is equal to the total heat that you are providing, okay, over the grams, the mass in grams into the change in temperature. So delta T is the change in temperature. So the unit for the specific heat becomes calories, small cals, or it can also be joules over grams times degree Celsius. Okay, so these are the units. Grams is the unit for grams is the unit for grams is the unit of mass is grams. The unit of change in temperature is degree Celsius. Heat is measured in calories or in joules. Okay, so so if it is so every substance has very unique. So the specific heat of water, let's look at it. Specific heat of water is 1.00 calories over the 1 gram of water degree Celsius, change by 1 degree Celsius and 1 degree, you know, 1 gram. And that is also equal to 4.184, 4.184 joules per grams degree Celsius. All right. Now let's look at the calculations using the okay, so there is another formula which also goes with it, which is the amount of heat. Heat is Q, stands for heat. And this heat is also equal to M. M is the mass in grams times specific heat. And the specific heat is calories per gram degree Celsius, or it can also be joules per gram degree Celsius, times the change in temperature. Change in temperature, and change in temperature is delta T, and that is T final, the final temperature minus the initial temperature. Okay, final minus the initial is equal to delta T. So let's look at some examples here. Okay, so here we have, okay, here we have, um, uh, how many, so page 81, okay, and that is problems, the study check 3.7. How many kilocalories? Kcals. So we are talking about heat. That is equal to heat. Always remember that. So that means it stands for Q. Okay. Are lost when 560 grams, so that is the mass, M, is equal to 560 grams of water. Okay. Cools from, so T final cools from, so this is the T initial, the initial temperature cools from, that was the initial temperature, 67 degrees Celsius. And final temperature cools from 67 to 22 degrees Celsius. Okay. So find the, how much is the value of Q? So the formula here is Q is equal to M times the specific heat times delta T. Okay, so here's your delta T value. Here's the delta T value. And the delta T value here is the difference in the two. So delta T is equal to actually T final minus T initial. And here's the thing, T final is 22 minus the T initial is 67. So the change in temperature comes out to be negative, which means the heat is lost. That is all it means. So this 45 degrees Celsius, negative. So this is delta T is negative. So don't worry about this negative number here. The only value this negative number has is that of heat loss. That's all. Okay, so that's one thing. Next is, now we know something. We know, since the question is talking about water and this is going to be given to you, the specific heat of water is equal to 1.00 cals over gram degree Celsius. So this is known or will be given to you. Okay, since the question is asking in calories, so that's what you need to put. I'm so sorry about this. I keep putting these on the, too many telemarketers bother. I'm sorry. Okay, so anyway, so let's do, the mass is 560 grams times 1.00. This is what, calories over grams degree Celsius times the change in temperature, 45 degrees Celsius. Okay, and that is equal to the value of the heat. So very important, you make a note of this formula in your handouts. Okay, and also make a note of this, the specific heat of water, which is always going to be 1. All right, that's all you need. And then delta T is the final, the change final minus the initial. And make a note that heat loss is just a negative sign, but it's not like used for subtracting or anything. That's what it is. So it's just a sign of the heat flow. So 560. Now grams and grams cancel out, Celsius and Celsius cancel out, and you're just left with the units of calories. So 560 times 1.00 times 45. What do you get? 25245. So the value of Q is 25245 calories. But the question is asking how many kilocalories. So we have to move further. So we know that 1 kcal is equal to 1000 calories. So the conversion factors are 1000 calories over 1 kcal, or 1 kcal over 1000 calories. Okay, so which one are we going to use? The ones that's giving us the calories on the top, this one. So we are going to take our Q value, which we just now formed, which is Q is equal to 25245 calories, multiply by 1 kcal over 1000 calories. Okay, so now you cancel out calories and calories cancel out, and you're just left with the cal. So 25245, now 25245 divide by 1000. And what do you get here? 25.2. So 25.2 kcal. All right. So this is how, you do this. So just keep this in mind that this is a very important formula, this one. So make a note of it and just pay attention to the details to use. If this is in calories, I mean, you could use the value for the joules also. That's not the case. If they were asking in joules, but our question was asking in kilograms. So pay attention to that. Next comes the heat of fusion and the heat of vaporization. And then just the last part. Okay, a little bit more and then we are done. All right, next is the heat of fusion and the heat of vaporization. Okay, 1 minute. Okay, thank you. Okay, so heat of fusion and the heat of vaporization. So first of all, look at this. When we say fusion, that means we are talking of melting. When we say fusion, it's melting. And when we say vaporization, that means we are talking about boiling. All right, heat of fusion and the heat of vaporization. This is the amount of heat. So look at this. H2O is the water. This water is in the form of solid, which means it is ice. Okay. The amount of heat this ice needs to melt is 80 point calories per gram. So 1 gram of ice would need 80 calories of heat. This is what it means. Okay. And this is going to give you, then once it absorbs that much of heat, only then the ice is going to convert to liquid water. Okay. Now the same thing, water in the form of solid, which is ice, when it absorbs 334 joules per gram. So 1 gram of ice will absorb 334 joules of heat in order to convert to water in the liquid form. Okay, so this is very important that you know how much of the heat is needed to bring about that change from a solid to a liquid state, from melt the ice to water, right? So in the joules, in the form of joules, and in the form of calories, that's the amount of heat. And this heat is called the heat of fusion. This heat is called the heat of fusion. Okay, this is one thing. Now, on the other hand, let's look at the The same amount of heat. Now here's a very important part. Water in a liquid form. If we need to freeze it and make it into water in a solid form, right? In other words, if we want the ice, so this is liquid water, and this is the ice, okay? So it will release, it is going to release 80 point, like exact 80 calories per gram of heat, or 334 joules per gram of heat. So here, keep this in mind, that the heat is released. If heat is a part of a product, that means the heat is released. And here, the heat is a part of the reactant, that heat is absorbed. Here, absorbed. But absorbed. Okay. But the thing is, to bring about this transformation from a solid to a liquid state, you absorb heat, and the same amount of heat is needed to convert the liquid back into the solid state. And in this case, it is going to be releasing heat. So this is important. So that's the heat of fusion. Then the heat of vaporize, the heat, calculating heat to melt or to freeze water. Let's do this problem. Yeah. Okay, let's look at this one. This is a study check problem. Study check. And that is 3.8. And that is problem, like problem 3.8, and page is 83, page number. Okay, so here in a freezer, 150 grams of water, okay, at 0 degrees Celsius is placed in an ice tray. How much heat in kilocalories? So kilocalories of heat. How much heat in kilocalories must be removed to form the ice? So you see, in other words, in this case, when we say heat is released, it also means that heat is removed. This is what it means. And it also means the heat is released. It means the same. Okay, so in other words, how much heat is being released? And that is going to be in the kilocalories. So we see that, first of all, the answer is in kilocalories. So we need to get it in calories. So 80. So we know that 1 gram is equal to 80 point calories. Okay. Where did I get that from? From here. From here. 80 calories per gram. 334 joules per gram. Okay, this is where we get it. So we are talking about the heat of fusion, like melting and freezing, both occurring at the same time. So this is what we have, 80. So this thing can be written as the conversion factors, 1 gram over 80 calories, or 80 calories, or 80 calories over 1 gram. All right, so we have here 150 grams times, okay, first get it in calories, 80 calories over 1 gram. Okay, and we can move further here. So we know that 1 kilocalories is equal to 1000 calories. So you are going to look at the grams, and grams cancel out, calories and calories cancel out, and you're left with kilocalories. So 150 times 80 times 1 divided by 1000. 1 times 1000. What do you get here? 12 kcal. Okay. 12 kcal. Okay. So this is how you use the heat of fusion and the heat of vaporization. I mean, this is the heat of fusion. Now let's look at the heat of vaporization. So here is this problem that relates to heat of vaporization. So the heat of vaporization is again the amount of heat that is needed to convert water from a liquid state to water in the gaseous state, vaporizing, okay? And how much of the heat is there? So the heat of vaporization, here you have water, H2O in a liquid state, right? You're supplying heat to it. And this converts to 540 calories per grams. Okay, or this also means 2260 joules per gram. Okay, so this is the amount of heat that is absorbed to convert water to a gaseous state. All right. All right, now the same amount of heat, if you have water that is in the gaseous state, that water in the gaseous state, when it condenses, when it condenses water in a gaseous state, when it condenses and forms water in the liquid state, it releases this amount of heat, 540 calories per gram, or 2260 joules per gram. Okay, so it's the same thing. The process is different. It's the same amount of heat that is bringing the physical transformation. Okay, now we are going to look at one problem here, which is a study check problem 3.9. Study check. Study check 3.9, page 86. Page 86, and this is the study check problem 3.9. Okay, so when steam from a pan of boiling water reaches a cool window, it condenses. How much heat in kilojoules? So we need to find in kilojoules. How much heat in kilojoules is released when 25 grams, 25.0 grams of steam condenses at temperature. The temperature given is 100 degrees Celsius. So this is like a steam condenses. So in other words, now here's very important here for you to like kind of pay attention to, is here very clearly we are looking at the conversion of liquid water to gaseous water that is becoming a steam, and vice versa, you know. So the heat exchange is the same on both the sides. And what is that heat exchange? That is this one, 540 calories per gram, or 2260 joules per gram, or opposite, you know, it's the same. Okay, so here we are now just going to do it. Write down what is given to you. You are given 25.0 grams of steam. So this is the grams of water. Easier way to write is like that, steam, times, the question is how much heat in kilojoules. So we need to find it in kilojoules. So we should do it first 1 gram, convert it first to joules, and then do it in kilojoules. So 1 kilojoule is equal to 1000 joules. And let's look at this, 1 gram, and how many joules is that? 2260 joules. Okay, so this cancels out the grams, cancels out the joules, and you're just left with the kilojoules. So 25.0 times 2260 times 1 divided by 1000. All right. And what do you get here? 56.5 kilojoules. Very good. Thank you, Tenzing. Thank you for all the mathematical pieces right here. Very good. Well done. Okay, so that's the amount of heat that is needed to bring the condensing. Okay, the next is the heating and the cooling curve. So let's look at this. Heating and cooling curve. Okay, so in this heating and cooling curve, we show the whole thing, this transformation on a graph. So on one end is the temperature scale, and this is the amount of heat. So this is the amount of heat that is being absorbed, and here is the temperature that increases or decreases. So you start with something, let's say 0 degrees Celsius is here, and then let's say 100 degrees here. And so this is a heating and cooling curve of water. So here's the thing, very important. So start from here, this, and then 1, 2, 3, and then you go up, and then like that. Okay, now, and then after this is like that. Okay, so there is a reason. Now here's, pay attention to this. This signifies the amount of heat that is being absorbed. You see that this is flat one row. That means that is, the temperature is not increasing. So this piece right here is the heat of vaporization. When all the water boils off, so I'm going to put HVAP. HVAP stands for heat of vaporization. And this is heat of fusion. This is H fuse, F-U-S. Okay. This piece right here is all of liquid. This is all of liquid. Let me change the color. Okay, let's do it in a different color. Okay, this piece right here is liquid. And this piece right here is gas. So you might be asked, on the test or something, that find out the, what are the label the phases. So all the solids, liquids, and gases are diagonal, kind of like flattened, but the straight flat are the heat. There is a reason. This very interesting piece right here I want to show. See, this one I made big. So all this is the amount of heat the liquid is going to absorb to go from a liquid phase to a gaseous phase. So all this heat is being absorbed. And similarly, this is the amount of heat that is needed to convert the solid to a liquid state. So here is, this is the amount of heat that that converts water in the solid state to water in the liquid state. Okay, and this is the amount of heat that is needed to convert the water that is in the liquid state to water in the gaseous state. Clear? Now there's another thing. This temperature right here is called a freezing point. This is the freezing point. So all the liquid, will all the solid, like all the liquid will convert into a solid in that particular, wherever that is pointing. So in this case, it's 0. And this temperature right here is the boiling point. Boiling point. Okay, so this relates to, let's just put it lightly, this relates to 0, 100, sorry. This relates to 100. So that's the boiling point. And this relates to 0. That's the freezing point. Okay, so another thing is there is a reason this piece right here is bigger. Let me just put it in a different color. This is bigger than this, because liquids, solids, because the particles are already very close to each other. Liquids a little bit further away. So a little bit heat transformation, and they convert from liquid to solid, or solid to liquid. But water, there is a big difference between how the particles are. It's all tying up back to your very first discussion, where we saw the water molecules versus the water molecules in the steam gaseous state. So the water molecules that are in the gaseous state are very, very, very far away from each other. So in order to make them very far away from each other, we need a lot of like heat. So that is why this piece is more. This part, this heat is the heat that brings the transformation from a liquid to gaseous state is more. So this is also called heat of vaporization, and heat of vaporization is larger than the heat of fusion. This is called HVAP. So this is the heat of fusion. Heat of fusion is less comparatively. So this is also shown as H fuse. Okay. So this is the heating and the cooling curve. Very easy. Just basically, you would be asked to find out, at what temperature is a substance liquid and what temperature is a solid, and so forth. And now, here you can leave out 3.11. It's like a mixture of like several different things. So you can leave out. I mean, I don't care. So it's leave out 3.11 page. This is an example, but you can study on your own if you want to. Page 88. Okay, leave out 3.11, page 88. The worked problems, sample problems. Okay. And study check problems. You can leave that. So this pretty much finishes your chapter. Very big chapter, but that is what it is. All right, guys. So here's the thing now. There is a thing that you will have a lab on this, and you will study about this more. Some phase changes, maybe a little bit, few extra things can pop up on the lab, but don't get scared, oh, we didn't cover it in the book and all that, blah, blah, blah. Certain things that you cannot cover everything from a book. You cannot cover everything in the lecture. That's why we have labs, so like a supplement. So you might see a few things like phase changes, like diagrams and all, but don't get scared. Those programs in Labster, they're designed for you to teach you. So just learn and go from there. Okay. So let me just stop.